and also the trans-Neptunian objects. As the name says, the trans-Neptunian objects are objects that have these orbits beyond the orbit of Neptune. And why we should care about the trans-Neptunian objects? First, from the distance from the sun, they are very far away from the sun. They had the space composition almost inalterate since the beginning of the solar system until nowadays. So when we are studying the composition of trans-Neptunian objects, we have access to the material that was in the protoplanetary disk at the moment of at that distance during the formation of the solar system. Also have objects with water ice. And the water by itself is a very important component because we still have doubts about how the water arrived on Earth and this whole for the presence of life. So the trans-Neptunian contains the keys, the answers of the formation and evolution of the solar system in many matters. But how could we study this population? Okay. So how can we study this population? First, this population comes with more than 3,000 objects. I thought that is much more about discovered so far. We have more than 3,000. Only 25 with names, 2,500 approximately with provisional names. The first one was discovered in 1992, and these objects, they are grouped according with the dynamical properties. So here in the x-axis, we have the distance from the sun, and in the y-axis, the inclination. So I told you that the trans-Neptunian objects, they have orbits beyond the orbit of Neptune, but that is a category called the centaurs that they had the origin on the trans-Neptunian region, but during the evolution of the solar system, they were scattered for more inner orbits. So those are the centaurs. We have the resonance objects that are the ones in red in the figure. The resonance are trapped in main resonance with Neptune. So Pluto itself is trapped in one of those resonances. So the objects in the same resonance of Pluto are called of TNOs, but we have also other resonances here. We have in blue the Kuiper belt itself. The trans-Neptunian region is also acknowledged as Kuiper belt because Kuiper was a scientist who predicted the existence of such structure beyond Neptune. So, but it's also acknowledged as classical belt. So here we have the objects that they are not too much on the influence of gravitational of Neptune, and they have low eccentricities. And in gray are the objects that they have much influence. They suffered much influence from Neptune, and they were scattered in the orbits. So the ones in gray are the scattered disk, and the size in these figures are almost in the scale. So I am an observational astronomer, so I will talk more about those objects from an observational perspective. One of the most used techniques to study that the astronomers use to study an object is the photometry. The photometry, we are just collecting the light, the flux that comes from an object, and that is an interesting technique called occultation. We do an occultation when the object passes in front of a star, so it occultates the bright of the star, and on that way we can have information about the size, the shape, the structure of the object. This occultation is from Charito. Charito is a centaur with had rings around his body, and those rings were discovered with an occultation. So here I can show you again. Yes. So here, the first spark is when the object, the first ring enters in the object, then the star is occultated by the main body, and then when the body is leaving another spark from the second part, and when they collect this occultation is like an international event. They may call it that they had a lot of research to participate, and as many participate, the occultation has more detail we can have from the body. So this occultation was done in 2014, and it was the first object, the first small body in the solar system with rings around him. It was discovered with occultation. Another approach is using photometry to study minor bodies in the solar system is using rotational light curve. So those objects, they are revolution around these axis around themselves in the sky. So depending on the geometry view, depending, for example, if we are looking for this body from the pole, we will not see any variation in the brightness of the object, but if the object is in an angle of 90 degrees, we will see the maximum variation in the brightness of the object. And if it was in an intermediate angle, we will see changes in maximums and minimums. And the amplitude tell us if a small amplitude we are looking for an object almost spherical. If it's high, if they have high amplitudes, we are looking for a body of a shape more ellipsoidal. And if we keeping collecting these light from enough time, you can discover the periodicity of the object. It means we can discover the rotational period of the object. And if we collect these light curves in different filters, we can have information about the surface of the object, if it has some kind of structure, if it has inhomogeneities. And in this case, it's the light curve of Almia. Almia here was observed in the VNR Johnson filters. So due to the maximum, the amplitude in the maximum peak, with the difference between the maximum peak, we can see that there are some kind of structure that was attributed to a dark spot on the surface. Here we are showing how this dark spot should be on the surface. So from photometry, we can have a lot of information from those bodies. We also have the spectroscopy. So I will keep the going. So spectroscopy is a technique. If photometry is a technique for we understand more about the physical process, the physical shape of the body. The spectroscopy is for understand more about the composition of the body. So the lights come from the object, hits the mirror of the telescope, and then the light is guided inside the telescope for a lot of ways, and it's put together until arrive to the spectrometer itself. We will measure these lights, and where these lights just come down. Depending on the position, we have signature of the composition of the material that is there. So the small bodies in the solar system, they don't emit lights, they only reflect lights, so we don't have emission spectrum, we only have absorbent spectrum. So I will show you here what exactly we see when we are in the telescope doing spectroscopy. So here it's the image that we see on the computer screen. So these vertical lines are emissions from the sky because we are ground-based observations. So those are from the gases in the atmosphere. The bright lines here, the horizontal ones, are the spectrum itself. Here we have two because one is for emission and another for absorption. As I thought, the solar system objects will have only absorbed light. So where the lights come down, it tells us which material is there. So in my case, I will have one of this kind, and not exactly that kind, because here we have more the shape, the profile-wise lines, and I have more absorption bands because I have more minerals and ions and combinations. So there are some challenges to use spectroscopy because as the trans-Neptunian objects are very far from the sun, they reflect not too much light. So they are faint targets. Faint targets generate low signal to noise ratio data. And when we go to analyze the spectrum, sometimes we have no signatures. We have only the spectral shape, the spectral slope to try to get some information from there. We have also the Earth's atmosphere because some of the materials absorb the same wavelength than the atmosphere. And when you have signatures, when you have features, we are talking about the largest TNOs. So is there an observational bias that we don't detect signatures for the small ones, or is lack of eyes? So the model of volatile retention, it says that bodies with less than 500 kilometers in the diameter, they are able to keep and retain the volatile that they are treated in the time of the formation, the formation. But the others with less than 500 kilometers, they are not able to retain these materials until nowadays. So because that we don't observe it. But we are really curious about the objects that are on the limits, or between those lines. For example, Chiron. Chiron has more than 1,000 kilometers, and we have some signatures of volatile bonding. So Chiron and other interesting is this one, 2004 BN 112, because it could have CH4, but it has 300 something kilometers in diameter. So what's happening in the limits of the size on the theory should be better understood. What else you know? We know about the geometric albedo. The albedo can be understood as the ability of reflect the light. So if an object has a low albedo, it is a dark object. But if it has a high albedo, it is a very reflective object, a very bright object. So here we have the albedo versus the diameter. And we can see no correlation because we have larger objects with high albedo, but we have also larger objects with low albedo. We have small objects with high albedo and with low albedo too, so no correlation between the albedo and the size of the bodies. Also, no correlation between the albedo and the slope in the spectral slope in the visible range, because someone could expect to see if the dark object has only very red spectral slope, very high spectral slope, or very low, but it doesn't happen. We have very finite spectral slope in objects with low albedo and medium albedo, so there is no correlation. I'd like to call attention to we have more than 3,000 TNOs discovered so far, and only 175 have those parameters measured. So we have too much to discover about this population. And we also have some information about the shapes. Some of them are very spherical, others are elongated, and that is also Arapov. Those ones are like models, and those are really pictures from the New Horizons mission. And these are out of scale. So Arapov is a very interesting shape because it has it's like a snowman. So it has like a head, a neck, and the body. And here you cannot perceive it, but it's really flat. So it's not so spherical as the figure is like flat. So it's a very interesting kind of shape that is also found in the trans-Neptunian region. And from spectroscopy, we also have a lot of diversity because, for example, Pluto spectrum shows a lot of signatures of methane ice with some positive detections of nitrogen and CO and carbon monoxide. But other TNO, Almia, it has a very, very well constrained spectrum too, but with signatures of water ice. in the amorphous and crystalline phase. Here, the signature in 1.65 is due to crystalline phase. So we have two trans-Neptunian objects with two different kinds of spectrum. And as I said, most of the spectrum of the trans-Neptunian objects, they have no signatures. We can only have hints here about the materials that are in the composition, in the surface composition, due to the drop on the reflectance, or due to, for example, here in 2005, RR43, we had clear signatures of water ice, but this then close to 2 microns. It's very close to atmosphere absorption, so it is the zone that it's bordered here. So in that case, it's a good case, but they have not too much signal. This spectrum is from Arrokoth. Arrokoth has only 35 kilometers in size, but this spectrum was obtained by new instruments. So here we have signatures of methanol ice in 2.27 and 2.34 with the shape of the spectrum here. We can have some hints about the presence of water ice, and we don't have the spectrum visible, but with the slope of the spectrophotometric points here, due to the red slope, we can infer the presence of some organic material. So from spectroscopy until 2.5 microns, it is what we have. But and after 2.5 microns. So we have a chance with IRAC. IRAC is the infrared array camera on board of the Spitzer Space Telescope. Spitzer was launched in 2003. IRAC was supposed to cover from 3.6 to 8 microns, but not continuously, with filters centered on 3.6, 4.5, 5.8, and 8 microns. It had an expected lifetime of 2.5 years, but it takes much more longer than that. In 2009, the cryogenic liquid was gone, so it started to operate in the hot mode. In that case, the channels 3 and 4 was gone, and you stayed only channels 1 and 2. And what you did was measure the flux in these two channels to see what information we could have from iron. So we used a synthetic spectrum of the materials that are supposed to be on the trans-Neptunian region in the trans-Neptunian object. And these dots are the convolution of the filter. So for example, here in methanol ice, in 3.6, it has a deeper absorption band. In the synthetic spectrum, it reflects in a low flux in relation with channel 2, 4.5. The water has the opposite behavior. And in that way, if an object has no information in the visible or in infrared, with those fluxes, you can have some kind of indication about what is going on the space composition. So Fernando Valenzuela and collaborators in 2021, they analyzed a sample of TNOs, and in the top box here, they have only objects with absorptions in the 3.6 microns in the channel 1 of the Spitzer, and more than 50 objects with absorption bands in channel 2. So they put in shape of maps the colors. We call colors the difference between filters. So the colors in channel 1 of Spitzer, and also the colors of the objects. So in that way, you can map which object has which material. So for example, OMIA, the technique works. So OMIA, it's knowledge because it has data from visible and infrared. So it's compatible with water ice. So OMIA is here in the region of the water ice. There are, for example, EDs and Makemake. There are also knowledge nodes, object node TNOs, and they have methanized in the space composition. So they are here too in the right place. And the others that we have no information, I have the first indication here about the space composition. And for example, here We have a lot of small objects, and it was the first time that they had something. We had something to say about this space composition. So my goal, a little bit of my work, is merge visible infrared and IREX pixel data to try to modeling the space composition of the trans-Neptunian objects. It's already a work in advance to JWST data, because JWST data will cover all those wavelengths, and now the only way that we have to access the information on those wavelengths is on that way. So it was a little bit of my job. Actually, the data that I used was not only one flux in RFC pixel data, but it was I did the measurement of the rotational light curve of a sample of objects in both channels. But the possibilities are unlimited, so because of that, we are applying nested sampling algorithm for Bayesian inference of the abundance of the materials, the size range, and which materials could be or could be not there. My sample was very diversified too, with two dark planets, Eris and Makmak. They are known of being dominated by signatures of methanized, but due to the shift of the center position of the methanized absorption bands, we suppose that there are nitrogen, there are two. Have the platinum Uya, it has an intermediate size, and his visible in infrared data is not well constrained, so we only have hints of the presence of water ice, methanol ice, and complex organics silicates on the space composition. And I also have the data from Chiron. Chiron, it is a very well studied object because it showed hints of activity in the past, and he already was considered as a comet. So Chiron has a history of variability of water ice in the space composition, and also emission of CN, CO, and CO2. So the first was Eris. So Eris has the redshift, visible spectral slope. Here signatures of methanized. Those are the flux that were measured with IREX pixel. I use also the albedo in the visible to eliminate models. So here we have the materials that were used to model Eris. So we have the spectrum of methanized, the spectrum of nitrogen, and I create some kind of, we call that inclusions. I put some organics material in a matrix of water ice, try to reproduce this slope here in the visible range. So my results, I was not able to find a model to compatible with the entire data, so I split that here in one micron. So to fit the first part of the spectrum, I need a little bit more of inclusions than to fit the second part of the spectrum. And in both cases, we need more nitrogen than methanized. It was already supposed by the literature. And in large grain size, in the order of millimeters grain size. For Makemake has almost the same constraints as Eris. So for Makemake, how it has a little bit more red visible spectral slope, we need a little bit more of the inclusions, but different from Eris, we need more methanized than nitrogen to model the data of Makemake. Uya, it's a little bit different because here we don't have clear signatures of the materials, but we have a drop. We have a drop on the reflectance close to 2 microns. A drop in the reflectance close to 2 microns in comparison with this region, so it's a little bit down here. So probably we have water ice here, and with the other drop after 2.2 microns, it could be due to some kind of hydrocarbons on its surface. Due to its low albedo, I put some dark materials too, as carbon. Due to the red spectral globe, I put some organics as triton and hydrogen. To try to fit this drop here with some methanol. And the water was included in the inclusions in kind of matrix with organics because we don't have clear signatures here of water. And our results were very well constrained. We have more than 300 models, and those are totally compatible and almost 4.5% of complex organics, 25% of the inclusions, 16% of methanol, and 54% of amorphous carbon. Chiron, we had two spectrum of chiron. They were obtained in different years. The gray one was obtained in 2004 and the blue one in 2005. They had different behaviors in this region of 2 micron. It's the region where the water is absorbed. So we decided to model both spectrum to see how this difference could reflect in the compositional models. So we used silicates as olivine and pyroxenes. We used amorphous carbon. We used water ice, and due to the shape here, we put methanol to see how it could fix the leader. And we had, with the same materials, we had two different proportions for the space composition of chiron. The one which had a deeper drop here in 2 microns, we had 26% of water ice. And the other one that has that low feature here in 2 microns, we had only 13%. It means in a time of one year, we had a difference almost of the half amount of water ice. And as the water ice comes down, the presence of silicates goes up. So only with JWST we can understand the whole of these materials, because we can see here after 4 microns, the shape is totally different, and also the band, the 3 micron bands in both spectrum are very different too. In that case, with a depth of almost 62%, and the other case almost 47%. So we don't have a way to access this difference, but with JWST we will have. So James Webb, it was launched in December of last year. It was built by NASA with contribution of ESA and the Canadian Space Agency. So the launch was successful. I'll stop talking.
Lifted off from a tropical rainforest to the edge of the sun itself. James Webb begins a voyage and the birth of the universe. Touching the holes through the clouds, this vehicle performance is nothing. The Ariane 5 rocket continues to fly uphill in nominal fashion. The rumble, the powerful Ariane 5 is here in the neutral 3D animation.
So here I'd like to point that the real orbit of launch and the modeled orbit was almost the same. So the launch was amazing, everything worked well. It was launched from French Guiana. The cost will almost $10 billion, and at the beginning it was thought like $500 million. And a little bit delayed too. It's supposed to be launched in 2007. It was in the end 2021. So life is like that. And in comparison with other space telescopes, Webb has a larger primary mirror with almost 7 meters in diameter. Hubble had like 2.4. Hubble has 2.4 meters and Spitzer less than 1 meter. And the temperature is intermediate between them. With JWST, we have access with high resolution to the wavelengths from 0.6 to 28 microns. And this range was not covered before. Also, in sensitivity, James Webb has much more sensitivity than Spitzer or Hubble. Here, the lower points means more sensitivity than the others, and also more resolution. We can see here by the amount of dots. So JWST came to revolutionize the science that you do. And now I will show you some of the results and the proposals of the solar system in JWST. So the proposal are separated into categories. So the ERS is earlier release science. Those projects, this category was created to the community, learn how web works in the practical way. So those data, the data obtained in the projects on that category, they have no priority time, so any people in any place of the world can access the data and work with it. The image of Jupiter were obtained with Mirkant, actually was in 3 filters, and in this image the filters are combined together, and this image is also corrected by rotational of Jupiter. So here we can see in the poles the aurora. I'm not a Jupiter specialist, I'm just like the image and like to show you. So but here you can see the bright auroras in the northern pole and also in the southern pole. The knowledge great red spot of Jupiter here appears as white because this image was obtained with Mirkant. Mirkant is in infrared wavelength, so in that wavelength, the images are the light reflected to the sun is kind of white. And we have a lot. I'm sure that this imaging has so much structure, so much size going on that were not possible to see before. My favorite image so far is from Neptune system. So Neptune has 14 satellites, and this image captures like 7 satellites of Neptune, and also the rings. So these data were obtained with the DDT, is the director time, and it's totally confidential about the project, but the data is there. And here is a close-up. So we know that Neptune in the images before was totally blue. So why Neptune is not blue in this image? Because in this wavelength, it's also an image from Mirkant. In this wavelength, the methanize is so active, it absorbs too much, then the object becomes almost dark. And these bright spots here and lines, they are due to clouds of methanize that they before absorb the methane, they reflect the sunlight. Because of that, we see they bright that much here. And we also have totally well defined the rings of Neptune. There are another category, it's the guaranteed time observational programs. In this category are the scientists and the science of the scientists that were involved in developing softwares and hardware and material from JWST. So they were awarded with GTO time. They have 1 year of proprietary time, and here I'm showing only the projects with TNOs or sensors or objects beyond Neptune that were awarded with time in JWST. I also had the GO, the General Observer Program. This program is open to the entire community to send a project to be evaluated and have received time to be done with JWST. And also in this category, the ones only with troublesome objects. I am working in this project that we receive data from Pluto, from Mirka, and MIDI also. MIDI is until 28 microns. And the last, but for me, one of the most important is the DISCO project. DISCO is discovering the space composition of TNOs, a large program for the JWST. It was the only large program approved in the cycle 1 of JWST, and the PI is Dr. Noemi Pinheiro Alonso. Here, I talk a little bit about DISCO. DISCO has 14 researchers from 8 different countries, 1 postdoc, me, and 2 PhD students. We were awarded with almost 100 hours in JWST, and we have a sample with almost 60 targets. Our targets, they are very diversified in size. Here we have pretty small objects and also large objects, and from different geometrical albedos too. We have very dark and almost neutral, not that bright objects. Our sample does not interlake with the other projects that are already being observed with JWST. And what we expect to see. So those are synthetic spectrum of materials and the signatures that should be observable in the resolution of the capabilities of near spec. So we have here the 3 microns absorption band of water ice. And we also have here in 4.27 the signature of CO2. Here after 3 microns, we have a lot of materials that are very active. So we hope to find signatures of those materials and also for new materials that we don't know that are there so far. So what we expect to see, it's hard to predict because JWST is amazing, it's incredible, so it can show us a lot of stuff that we still have no opportunity to see. And so it will review the composition of the solar system until 28 microns. And it will help us to understand better the origin and evolution of the solar system. And for us, it will bring a lot of new detections. Thank you so much.
All right, thank you. Okay, if you have any questions for the presenter today, I'll give priorities for the online participants. Please type in or raise your hand. Okay, any questions from the room? Go ahead.
It seems like there's a lot of more or less classification based on the data to determine, what composition at a certain wavelength something is. Is there research or any idea how techniques such as like AI machine learning can be applied to help ease some of that computational load?
Yes, so this is the part of we are Mario is taking a part. Actually, the machine learning is helping. IA is helping us in the matter of selecting the most important materials because, for example, here, for example, this spectrum here of Makemake. We have, if I was modeling this object, I will put methanize, do it to this absorption lens. I will put some kind of dark material because due to concern about the albedo, but I had a lot of possibilities to do that. So the machine learn evaluates the space of parameters. It does evaluate the final result, but the input parameters and see the best constraints of each for each spectrum for each data. And it is helping us a lot to modeling the objects because by myself, before we are working with this code, by myself, I take like months to modeling one object. We received 60 objects in 1 year, so we had to do that in a fast way. So machine learning is IA is doing that for us.
Any other questions? I think I have good questions. With the disco, you said you mentioned okay, 60 round objects. Are there like all new objects or some of your new objects?
No, of our entire sample was selected from object that we have some knowledge before.
Okay,
Like
all the objects are pre-selected.
Yeah, exactly, were pre-selected and they have at least the diameter and the albedo measure. In some case, they don't have information in visible and in infrared range, so we are putting proposals in a large telescope to have something before prior the JWST data to compare to put together to help us.
Okay, I think I have one more. So, all these TNO objects are they all related to the formations of the solar systems, or are there recent like a new newly formed objects too?
No, I don't think so, because the thing is when you have in some object that they are pretty new, or if they're pretty new, it's because they suffer some kind of collision that parts one old object in small pieces of a new object. And if they came from outside of the solar system, they enter in the category of interstellar objects. So they only pass from here and go outside. The last 2 years, we saw a couple of those kinds of objects. So the TNOs, they are very pristine, they are very primordial in the solar system.
Okay, all right, thank you.
You're welcome.
Any other questions? Looks like none. Okay, let's thank the speaker again, and thank you.